Hello everyone, I'm Max and welcome to our very first math lesson, Numbers and Operations. Today I will explain what numbers, well, not what they are because you probably know what they are divided into as groups or classifications. Then I'll go into key properties of said numbers and operations between them. After that I'll mention or explain PEMDAS or for order of operations, so you know how to actually solve given equations. After that, we'll go into prime factorization, the greatest common divisor, and the least common multiple. Well, let's get started. First off, the smallest group of numbers, well, you can't compare infinities, but the most basic group of numbers is natural numbers. This is the symbol. There's also another one that looks more like the word in, but I'll stick to the first one for the rest of whatever I'm writing. They are counting numbers, 1, 2, 3, 4, etc., etc. Some definitions include 0, but most begin at 1 because they are the numbers that appear in nature. And since 0 or the lack of doesn't appear directly, we will put a different group of numbers which will never be mentioned after this. Whole numbers, which are basically just natural numbers with the 0. Next up are integers. They have this fancy, oh my god, this is not very fancy. A Z symbol. Either of these two is fine. I won't nag you about writing them. Your teachers probably will. But they are negative natural numbers plus 0 plus natural numbers. Basically, -3, -2, -1, 0, 1, 2, 3, etc. in both ways, of course. So take natural numbers, mirror them over 0, and take the entire group you got. That's the integers. Also, fun thing, the letter Z for the symbol comes from the German word zahlen, which means to count, or counting, or depends on the context, basically, yeah. Which is unfortunate name because it could be for natural numbers. But I did not make this stuff up. Someone else did decades ago, probably. After that, we get to rational numbers, which the symbol for is Q, or this Q, one of these. I will primarily use this one. They are numbers that can be written in the form of a fraction. Basically, one number divided by the other, where b must not equal 1 or 0, because you cannot divide by 0, and because dividing by 1 is kind of pointless. So let's just agree that b can be any number except 1 and 0. Also, they have to be integers, so you can have a fraction of a divided by minus b or something. I don't mind that, as long as they are round numbers, which means they don't have decimal points, as in 3.2 divided by 1.5, okay? A fraction would be 3/5, for instance. Now there's a fun little trick how to know if a decimal number is rational or not. This only works for repeating numbers, like 0.3, which repeats periodically, as is 0.3333333. We know that that is equal to 1/3. But how do we know that? And why does 0.9, which should be 3/3, not write itself as 1? Is it 1 or is it not? So, to start, we will write 0.3 as x, and on the right side the same for 0.9. Now, per rule of equations, if we multiply one side by a number, we have to multiply the other one as well. So we will multiply by 10, so we get the repeating factor out. So 3.3 repeating equals 10x. For instance, if it was 3 decimal places repeating, like 0.325, you would multiply by 1,000. Now, we do the same thing for 0.9, we get 9.9 is 10x. Now we take 1x away on each side, on both equations. On the x side, so the 10x, we get 9x, and on the left side, since we don't have an x value there, we'll just use the value we determined for it, so 0.9 periodically. And since infinite number of 9s cancel out the other infinite number of 9s in the decimal spots, we will get 9.0. And on the left, we'll get 3.0 equals 9x. Now, if we divide both sides on both equations with 9, we'll get 3/9 equals x and 9/9 equals x. So 3/9 is 1/3, which proves that 0.3 repeating periodically is 1/3. But 9/9, that equals to 1, which means that 0.9 periodically would have to equal to 1, which it does, and this is a little neat proof, but you can use this to write any number that has a repeatable part in its decimal spot as a fraction. Also, don't be distracted by this. You can also take away different values of x. For instance, if the number started as 3.25325, you can multiply by 100 and take away 1/100th of an x. Up to you, you can do it any way you want because the ratio or the fraction will always be the same. Next up are irrational numbers. I will use IRR for them because I don't remember a symbol. They are the good numbers like pi or root of 2 or many other roots that you can't quite calculate for. Of course, root of 4 is 2, we all know that. But how do we know a number is irrational? Well, for root of 2, square root of course, there is a very popular proof by contradiction, where you start by assuming that it is rational, so it can be written in the terms of a divided by b, where they are co-prime integers, which means that they have no common factors beside 1. So if you listed all the numbers that a can be divided by, and all the numbers that b can be divided by, the only numbers that are the same are 1. Meaning that they cannot be divided by any other number. Now, after that we can square both sides. We get 2 equals a squared divided by b squared, and we order the numbers around, so we get 2 times b squared equals a squared. Now we see that a squared must be even, because there's a 2 next to b squared, and since 2, if you multiply any number by an even number, it becomes even. So we know that a squared is even. If you take an odd number and you square it, like number 3 or number 5, it becomes 9 or it becomes 25, which is still odd. But if you take a number that is even, like 2, 4, 6, you get another even number, which is 4, 16, and 36. That also means that a must be even as well. Okay, we're getting somewhere. So we can write a as 2 times k. We put another number, which is not important for the sake of this argument, because whatever the number is, if we multiply it by 2, as long as it's not 0, we get an even number. Okay, so we will write the left side of the equation, and instead of a squared, we will write the squared value of 2k, which is 2 squared k squared. And now we can divide both sides by 2. We get b squared equals 2k squared. And now we're in the same predicament, because that would mean that b squared is even, which results in b being even. But we made an assumption that the only divisor between a and b is 1. So if we have another divisor, which is 2, it contradicts our original point, which means this contradiction is our proof that square root of 2 is irrational. I hope this made sense. I can post a comment or in the description the website or something where it's more clearly written, but I do hope that you understood this. Next off, we can move on to real numbers, for which the symbol is r. They are all rational and irrational numbers combined. Basically, if we were to represent numbers on an axis or number line, for instance 0, 1, 2, 3, you would get all rational numbers by halving a distance between 2 of chosen points you already have. For instance, between 0 and 1, you get 1 rational number, and then half the distance between 1 and that, you get another one. Keep doing that, and you will fill up the line with a lot of numbers. But there will still be a tiny gap, because you can't completely fill all of the space. That is where the irrational numbers come in. Together, they form the group called real numbers. So basically, real numbers are all numbers that can be represented on our number line, or real number axis. And if you were to diagram this, natural numbers are a small group. If you add 0 to that, you get whole numbers. If you add negative numbers, you get integers, if you add fractions, you'll get rational numbers. There's a separate bubble for irrational, which are, of course, pi or square root of 2. And if we group all these together, we get real numbers. However, there is also one little, well, not so little group, and there's more than one, but one more that I will mention and further dive into later on. They are complex numbers. Some say they are a separate bubble. There are very few people that say that, because they actually encompass the entirety of real numbers as well. And how do we know that? Well, let's say this is the real number or the number line. 0, 1, 2, 3, whatever. For complex numbers, you add another dimension to that with I as a unit. And any number anywhere in the space is complex. They are, for instance, take any real number like 2/5, add on certain value of i's, and here can represent any number, any real number. So it can also be 2/5 plus 2/5 I. That is a complex number. 2/5 can be a complex number. 2 can be a complex number, with the I, or imaginary unit, being 0. But we will dive more into that, why they are the way they are, what I means, what's imaginary number. We will get to that in the lesson of complex numbers, which can be known roughly when from the channel introduction I made 2 weeks ago, yes. Next up, we have key properties of numbers. First, we have commutative property. I do not know if I said that correctly, but what it states is that the order does not matter for addition or multiplication as long as all those numbers or operations are of the same group. Meaning if we have only pluses, 3 plus 5 plus 3 plus 5 plus 4, we can take any two numbers and add them together, even if it's a 3 plus 4 or 5 plus 5, or either combination works, regardless of the order we write them in. Same for multiplication. 2 times 4 times 3 times 10. We can multiply any of the two and get the same result, as long as we keep the rule that we don't multiply 2 with 4 and 10 at the same time. For instance, we would multiply 3 and 4, and 2 and 10, we would get 20, and 12, we would get to 240 as a result. The order, however, does matter for subtraction and division, because 2 divided by 5 is definitely not equal to 5 divided by 2. However, division has a little neat property, which is much more useful in graphing and complex numbers, and it's called an absolute value. It's represented by this sort of bracket. You put the number or an expression in it, and what it does is that the output is always positive, meaning that if the x is less than 0, the result of this bracket would be negative x minus x, because that would put the overall value as a positive. So if it's a minus 3, it would become minus minus 3, which is 3. But if the x is greater than 0, well, the bracket don't do anything. They just keep the value as it is, uninterrupted. This value actually means the distance between the two. So usually there's a minus sign between the numbers, so it's 5 minus 3. It's not equal to 3 minus 5, because one equals 2 and the other one equals negative 2. But the absolute value kind of says that what the bracket would say is that if you write this expression or this expression, the brackets mean the distance and minus means between. So the distance between the 0.5 and 0.3 is 2. And distance always has a positive value. And since the distance between 0.3 and 0.5 is also 2, because we don't go into negatives, we have the same result. However, if there's a plus sign, 5 plus 3, this would mean the distance between the value 5 and the value negative 3, because minus states between. Okay? Which is why this value is much greater. For instance, if we graph this on a line, we can say 2 plus 1 2 minus 1, and let's say minus 1 plus 2. Okay, in first case we have this and this, because we have to rewrite this as a form of negative in between. So it's 2 minus minus 1. The distance between them is 3. 1, 2, 3, which is the result here. In next case, we have 2 and 1, because minus means the distance. Distance here is 1. In the last case, you can do different order operations if you treat numbers that whatever the sign in front of them is their property. We can rearrange this. For instance, we can put 3 to the right and 5 to the left. We have minus 5 plus 3 plus 3. It still obeys the rules, because the order is not as important. If we added on multiplication, we would have to treat this box as a separate entity, to which we will get to. But yes, we can move these two around, which gives us 2 minus 1 in these brackets. Or we can just do the same thing by taking negative 1 and negative 2. The distance is 1. Same as here. If we take 2 and 1, the distance is 1. That's a fun little trick you can use with absolute values, but it's not as important as we would... It's not as important yet. Anyway, next one is associative property. It states that grouping doesn't matter for addition or multiplication, meaning that if we have 2 plus 3 plus 4, we can group this any way we want, 2 plus 3 plus 4, or 2 plus 3 plus 4. The result will be the same. This only states for addition or multiplication. Next one, we have distributive property, which states that multiplication distributes over addition. Let's write this in 3 times 2 plus 5, and in general terms that is a times b plus c. Now let's solve this first. 3 times, which is that 7, equals 21. And now let's use what we learned here, that it distributes over into ab plus ac. If we do that, we get 3 times 2 plus 3 times 5. If we add 6 and 15, we get 21, so they are the same, which means that this is the general formula for distributive property, which is very useful because once we get to more complex things like equations with different variables, let's say 25x plus 5 equals 0, we can take 5 away by the same property in the other direction, which gives us 5x plus 1 equals 0. We can cancel this 5 out because dividing 0 by any number is still 0. And this will give us this much more simple equation to work with. Moving on, we have the identity property. The identity property states that there are special that do nothing numbers. For addition, additive identity is 0, so any number onto which you add 0 is the number itself. As for multiplication, any number multiplied by 1 is itself. So this is additive identity, and this is multiplicative identity. Next up, there's inverse, which is the last one of the properties, which states that every number has an opposite additive inverse and a reciprocal multiplicative inverse. For the opposite inverse, or additive inverse, sorry, we have 5 plus negative 5 equals 0, so any number onto which you add the same number but with a different sign in front of it, the result will be 0. And for multiplication, the reciprocal version, I think that I said that correctly, is basically the same number like 4, but a fraction where 4 is under the division line. And that will always result into 1. So a times 1 over a is 1. And that is the last of the properties, which means we can move on to the order of operation. The most common term you'll hear is PEMDAS, which states for parentheses or brackets, exponents, like a to the power of x, multiplication or division, a times x, and addition or subtraction, a plus x. Now, if we went to solve an equation by following PEMDAS, we would say, let's think. Okay, 2 plus 3 in the brackets times 2 to the power of 2 divided by 3 times 3 plus 1. I think this covers all bases. First off, we have to solve for brackets. If we do that, we get 5 times 2 to the power of 2 divided by 3 times 3 plus 1. Of course, if we're going step by step, this is the correct way to do it. If you're on the next level, you could have put 3 already here or cancel it out because you know what happens next. Of course, exponents can be written as multiplication and we could do 2 times 2, but since we didn't do that, and because in many examples you will solve later on in life, you won't be able to do that because you'll have logarithmic functions in the exponent and you have to actually calculate the value, and it's not. It will be more close to 2 to the power of 2 times 2.4, which you can't really graph out. Well, you can graph out, but you can't write out that simple in a simple way. So next is exponents, which is this, which, as I hope you know, exponents mean the amount of numbers multiplied by themselves, meaning 2 to the power of 2 is 2 times 2, which is 4. Now we have divide by 3 times 3 plus 1. Next up is multiplication and division. Since this is division line and this is multiplication, as per rules of multiplication and division of rational numbers, let's say a divided by b is 1 and the other one is c divided by d, and then we divide ab divided by b this. For multiplication, you just multiply top with top and bottom with bottom, so you get a times c divided by b times d. As for division, there's a neat little zigzag rule. You can multiply like this. The bottom number goes with the top number, and the bottom of the top number goes with top of the bottom. So basically, if you had it written in the form of a b divided by c d, and they both give you the same result, a times d divided by b times c. By that logic, we can put 3 on top of the division line, which would give us 5 times 4 times 3 divided by 3, plus 1. And since we don't have to multiply, we can just cancel this out, because division has the same priority as multiplication. We get 5 times 4, which is 20, plus 1, which is our beloved 21. Next up, prime factorization, or how I'll call it, PF for short, with which we will learn how to determine the greatest common divisor and the lowest or least common multiple. First, what are prime numbers? Prime numbers are the numbers that only have 2 numbers dividing them, and that is, let's do this. This is the divisors of number x, and they are 1 and x. This is the general form for prime numbers. So put the x in here, and that's how it works. For instance, we know that a prime number is a 7, so the dividers of 7 are 1 and 7. And now, breaking down numbers into building blocks, or primes, works somehow like this. We have a number like 100, or actually, let's say 30 and 45, which will be very useful for the demonstration. Let's get the units down. First of all, before we do that, the rules for division. You can divide a number by 2 if it's an even number. How do we know? The number on its last digit, for instance 2, 5, if the number's last digit is 2, 4, 6, 8, or 0, it's divisible by 2. For 3, the sum of all these parts, so 3 plus 2 plus 5, which is 10, must be divisible by 3, and the number is divisible by 3 itself. How do I know that quickly? 325 is not divisible because the sum is 10, as I said. Division by 4. If the last 2 numbers, so 325, if the last 2 numbers are divisible by 4, then the whole number is divisible by 4. 25 is not, 24 is, so 324 is, 325 is not. For 5, in this last spot, you have to have either a 0 or a 5, pretty simple, pretty standard. For 6, the number has to be both divisible by 3 and 2. So you have to have both of these rules at the same time. So it ends with one of these 5 numbers, and the sum overall has to be divisible by 3. There's a rule for 7, which I won't dive deep into because it's quite complex and I genuinely forgot it. So let's move on to 8. For number 8, if the last 4 digits, or however you call it, are divisible by 8, the number is divisible by 8. Well, the last 3, sorry. If I said 4, it's the last 3. So 1080 is divisible by 8 because 080 is, you can divide that by 8. It's basically a stronger rule than for 4. Next up, and last one, is number 9. If the sum of all the digits, for instance, 1080, if the sum of them is divisible by 9, like with a 3, then it's divisible by 9. So this one is, for instance, 3149. If we sum them up, we have 7 and 10, which is 17, and if we do that again, we get 8, which is not. However, if we change either of them for 1 up, you would get it. So let's say we can put 4149 or 3249 or 3159. They all sum up to the same value. They all sum up to 18, which is divisible by 9, because 2 times 9 is 18. Or if we sum that up again, we get 9. So yes, all of them are divisible by 9. Now back to the important part. We separate numbers into their primes. So we find the lowest prime we can find. The first one is 2. Also, how to determine if a number is prime. So for 30 and 45, let's say 30 has 2, which gives us 15. Okay, these both have 3, so this 3, 3. 15 gives us 5, and 45 gives us 15. Since we were here before, we can do the 3, 5, 5, 5, 1, 1. And these are our prime factors. So we can write the number as 30 equals 2 times 3 times 5, and 45 equals 3 squared times 5. How to actually get the greatest common divisor or the lowest common multiple for the GCD. Since it's the greatest common divisor, which is a number that is lower than both of them, we will take only the factors that appear in both, and if they appear with different exponents, we will take the one with the lower. So we scan, okay, does a 2 appear in both? No, it doesn't. Okay, we don't write it down. Does the 3 appear in both? Yes, it does. It's a 3 or a 3 to the power of 2. We will take the lower power of just 3. Multiply that with 5 because it's also present in both, and we get 15. Now for the lowest common multiple, I think that's the wrong one, yes, we do the other thing. We take all of the prime factors and if there are multiple of them, we take the one with the highest exponent. So we go by 1. Is there a 2? Yes, there is a 2. We take the 2. Is there a 3? Yes, there's 2 3s. 3 and 3 to the power of 2. We take 3 to the power of 2. And after that, we have a 5, which gives us 90. The long way, you have to go write out all the factors that divide the number. For instance, 30, 45, and 90 equals, of course, 1, 2, 3, 5, 6, 10, 15, 30. For 45, we get 1, 3, 5, yeah, no, I think it's a 9, 15, and 45. You may be asking how I wrote them out so fast, like even for 90. Go 1, 2, 3, 5, 5, 6, 9, 10, 15, 18, 30, and then 45, and then 90. And if you're asking yourself how I did this so fast, there's a neat little rule. Once you get the numbers that that are together, one behind another, that when multiplied give the number itself. For instance, 5 times 6 is 30, 5 times 9 is 45, 9 times 10 is 90. Once you get there, you can just do the same thing for all other numbers. So 6 times 15 is 90, I'm pretty sure. 5 times 18 is 90, 3 times 30 is 19, 2 times 45 is 90. This is just how you do it. And now, how do we know that the greatest common divisor is 15? When we go like this, and we compare what they are. Okay, this is a 30, this one does not have a 30, so we go 1 down. 15, okay, this one does have 15, so 15 is the greatest common divisor. As for the multiple, well, you just, other than just trying different numbers to multiply them each by, or just listing the multiples out by going like 30, 60, 90, and 45, 90. I think this is the easiest and the fastest way, especially when you get to go more complex numbers like 2, 3, 7, and 4, 5, 9. Could you do this instantly? Most probably not. Well, this sums up today's lesson, and now follows a quick little test, which I will just share on the screen. So if you want, you can pause, you can screenshot or whatever, and solve the test. Thank you, everyone. Have a good day, and see you on our next quest.